Okay, good afternoon, physics students. We're going to pick up where we left off last week. We're going to talk about Ohm's law. Ohm's law, named after Ohm. He kind of came up with he figured out that there was more than just voltage and current. His name was Georg, by the way, Georg Simon Ohm. And he did this in the early 1800s. If you were wanting to be a discoverer of like fundamental things, you had to be born or had to be working in the 1800s, it seems like. But anyway, the symbol for the ohm. So ohm, what he added to the relationship between voltage and current was the ohm, right? And it is a unit of resistance. And it kind of looks like that. That is the units that we use for that, okay? And so back on Thursday, we said that current, which we're going to use the letter I, is equal to volts over resistance, right? And if we look at that in terms of our units, it's going to be amps is equal to volts over ohms, okay? So remember that voltage is the electric potential, right? The potential difference from one end to another. It's the difference across a circuit. Okay, so from one end might be low pressure, the other end is high pressure, or negative to positive. There's a difference in the potential, okay, and we get a current going through that circuit. But let's kind of take a look at Ohm's law a little bit in practical purposes, I suppose. But anyway, let's just say that the relationship is that 1 amp is equal to 1 volt over 1 ohm. Okay? And that's how I'm going to draw I'm not going to draw the fancy omega like I did over here. Okay? So let's just say that we're talking about a 12-volt battery, right? So if we have a 12-volt battery and we still only have 1 ohm of resistance, well, that's going to produce 12 amps of current flowing through that circuit. Okay, so resistance plays a big role in how much current there is because the voltage is not going to really necessarily change. Okay, so for example, in terms of real life, the resistance of a lamp cord, right? So when you plug in a lamp or something like that, is less than 1 ohm, right? There's not a lot of resistance there. Okay, so you're going to get a lot of good current through there. But an incandescent bulb, which is your normal little bulb that looks like this, right? An incandescent bulb has a resistance more than 100. Okay, and so that's going to really slow the current down as it's coming in and feeding that light bulb, and then when it leaves, it's it's going to pick back up again, but it's going to be slowed by that light bulb. Okay, most of your electrical appliances, like a toaster, an iron, quesadilla maker, those are going to be anywhere from 15 to 20 ohms of resistance. Okay, so another way we can kind of manipulate this formula is to say that voltage is equal to amps times resistance, and that might come in handy depending on the type of problem that we're dealing with, right? We can manipulate that any way we want. It can look like that as well. Okay, so Ohm's law, named after Mr. Ohm. Now, let's talk about shock, right? So shocking has to do with the voltage, right? The electric potential and the current. But in a given circuit, the voltage is usually set, all right? And so the current is then going to only be based on the resistance, okay? So let's put this back up here. Current is equal to voltage over resistance, okay? And so let's talk about how, as a human, can I get shocked or not shocked, right? So the range of resistance in the human body, okay, is anywhere from 100 ohms to 500,000 ohms. Okay, now what determines that are things like the salinity of your skin and also the moisture content of your skin. Okay, so that's gonna dictate how much resistance your body has. So this has less resistance. So this would be like salty. What would I want to call it? Wet skin, right? If you're swimming in the ocean, you don't have very much resistance. Your body does not have very much resistance. It's going to flow in and around you, right? But if your skin is very dry, okay, then you're going to have a lot of resistance and not much current can flow through you, okay? Now, a 12-volt battery, right, it doesn't really hurt you a whole lot unless it's got a huge amount of amps. Some car batteries, if you were to touch the positive and the negative together, it could you'd feel a pretty good jolt because it's got a lot of amps. Even though it's just a 12-volt battery, it's going to have a lot of current flowing through there. Okay. If your skin is wet, however, right, then you're definitely going to feel it. Okay. So let's take a look at some values. If your current in amps is 0.001, sorry about that, then you're not going to really, you're going to barely feel that, okay? If your current goes up to 0.005, okay, now that's causing some pain, okay? If it goes to 0.010, you get some involuntary muscle contractions, like you might see in a taser. Okay, and then if we go up another 5 milliohms or amps, sorry, you lose muscle control. Okay, and if we go up to 0.070, which I jump up there, possible death. Okay, and again, this is a lot dependent on the current state that your skin or your points of contact are, right? The higher your resistance, the smaller these numbers will be. Okay, so in the United States, we have most of our household currents, circuits are 120 volts. Okay, and so, you know, if you touch a bare wire, okay, let me just kind of give you some other practical information. You're going to do more damage if you touch, let's say that you were dumb, which luckily none of you are, and you had 2 forks or 2 knives in your hand, okay, and you went up to your wall outlet, right? It looks like this, right? Okay. And you stick your knife into one end, right? You stick your knife in. Let me get a different color here. If you stick one knife in there and one knife in there, now you have completed the circuit. And if you have one knife in your left hand and one knife in your right hand, that circuit is going to go through your left hand, through your body, through your heart, and out your right hand, okay? Whereas if you were to just take one hand, right, and use like your thumb and your forefinger, your pointer finger, right, to go across these 2 points here, then it's only going to go through your hand, right? The circuit is going to follow it's not going to go all the way up your arm and then come back down that same arm. It's just going to make a little circuit through your hand. So if you ever have to test something, right, and you have no other way, this is really dumb, but just use one hand, right? Use 2 fingers instead of 2 hands because you're going to do less damage that way. Okay, but anyway, let's say we have 120 volts. Now we do have people that die every year from common household electrical problems. So if you have a bare wire somewhere, okay, and if you're touching the ground and you touch that current or touch that wire, that current is going to go, it's probably not going to do much harm because the plugs are what we call grounded. But obviously if you're standing in a bathtub with water all around you, and that water is connected to metal plumbing, right? Now you've created a great path with low resistance to the ground. And so that voltage, that current is going to flow through you very easily. And there's going to be a lot of current that flows through you very easily, okay? And with low resistance, and it's going to do some serious damage, okay? So that's let's just kind of look at a scenario. So my current is going to be 120 volts. Like if you only offer up 200 ohms of resistance, right? If you do the division, let me do that real quick. 120 divided by 200 is 0.6, right? So if you're standing in a bathtub and you only are giving up that much resistance, you're dying, right? Because look at your amps, and remember the chart that I just told you. Anything over 0.07, right, is going to kill. It could kill you. So 0.6 amps, definitely going to kill you. Okay, so keep that in mind. That's why they make it's kind of a joke, but not really, about being wet, right? You don't want to touch a switch that has water on it, stuff like that. Okay, all right. Now remember that in order for there to be a shock, in order for you to get shocked, there has to be a difference in electric potential between you and between two parts of your body. Okay, now if we're dealing with a household outlet and you go left hand, right hand, there's definitely gonna be a difference because one's positive and one's negative. Okay, kind of. All right. Now, if you were on a building and you were Spider-Man and you were falling for some reason off that building, if you reached out and grabbed a wire, an electrical wire, connected between two telephone poles, and you grab that one wire and that's all you touched, you're not going to be shocked because there's no difference in the potential. You're grabbing the one wire that has one potential, right? Now, if you grab another wire that has a different potential, now current will flow, and that's when you die. Okay, if you were to touch, had one hand on the wire, if you put both hands on the same wire, you don't die. You don't even hardly feel a shock because it's the same voltage from your right hand to your left hand. It's only when there's a difference from right hand to left hand that you're going to get shocked, right? This is why birds can hang out on a wire, because they're on the same wire. Okay, now if they happen to slip up and they start to fall and they have one foot on one wire and a wing on a different wire that has a different voltage, they're going to get electrocuted. Okay, so that's a very key point, is that there has to be a difference in electric potential in order for charge to flow. Okay, all right. Now let's talk about real quick an electrical cord. One nice thing about that. Okay, let's see how well I can draw this. You've probably seen this before. We have the rounded part, and then we got the parts that you plug in, right? Okay, so these two prongs here are the ones that are actually carrying the current. Okay, one is what we call the hot wire and one is called a neutral. Okay, but that rounded wire is called a ground. And that every wire in your house should have a ground that is actually connected to a piece of copper that is running outside of your house and actually into the ground. Okay, and that's why it's called a ground. Okay, and this is a good thing because this helps eliminate some of that electric potential. So if the electrical appliance, right, is actually connected to all three wires. Okay, so if the live wire accidentally comes in, hold on a second, sorry. If the live wire comes into contact with the metal surface of the appliance and you touch the appliance, you would, if there was no ground, that electricity would flow through you into the ground. okay? But because the appliance is what we call grounded, right, because of this guy, that difference in potential is then sent into that wire, and it eliminates some of the electric shock, okay? Um, so any type of electric shock, we're dealing with resistance, and usually resistance causes heat, right? So when people have an electric shock or electric current or something, they're going to do some damage to some tissue. They're going to burn some tissue right there. They could stop their heart, right? They could stop their lungs, all that kind of stuff. And so when somebody does CPR, and then they use the little paddles to administer a shock, sometimes that's good for getting it started again, right? So electricity can stop your heart, or it can start it back up again. Now, when we talk about plugs and this type of thing, most of the time we're talking about what we call AC, right, which is alternating current. When your house, right, is alternating current, and we'll talk about that in a minute. And DC is what we call direct current. And direct current is pretty much what you get from batteries. Okay, AC is what you get from generators. Okay, and we'll talk about how that works in a little bit. Okay, now what does it mean by direct current? Direct current means it only flows in one direction. If you think about a battery, right, a car battery that has a little positive terminal here and negative terminal here, right, the electrons flow in one direction, right? If we're connecting them with a wire or whatever, they're going to flow in that direction, right? And they're only going to flow in that direction. Okay, so if we were to look at a graph of current over time for a direct circuit, right, it's just like this. That's it. But an alternating current, if we were to look at its current over time, it would look like this. Okay, it's sometimes going to be positive, sometimes going to be negative. It's flipping back and forth, back and forth, back and forth. Okay, the reason for this is because we can carry large voltages this way a lot safer than we can with direct current. Okay, and so it's, that's the main benefit of AC current. Okay, almost all residences, all commercial, everything uses that same voltage, and the frequency at the up and down that I drew here is happening at about 60 hertz, right? So 60 cycles per second. All right. Now it could be a little bit lower than that, but this is roughly the frequency that is used. Okay. Um, so again, we use AC current because the voltage can be stepped up or stepped down rather easily versus direct current. Okay. Now, in the United States, actually in North America, the common voltage is 120 volts. Okay. What they found out though in the early days of electricity, anything that had a higher voltage than that actually burned out the filaments in the light bulbs. So if you look at a light bulb, right, it's got a little wire that comes up and then it kind of does this little thing and it comes back down. So that's called the filament right there. And that filament would burn up pretty easily if the voltage went above that. So they made all the electrical factories or electrical generators were made to actually do 110 volts. Okay, and we've now stepped that up a little bit with technology advances, but they first started at 110 volts. We currently are at 120. Okay, so any electric generating station before 1900 would be at 110 volts. Okay, in Europe, electricity came along later, and so they kind of had the benefit of what was happening in North America, and they actually used 220 volts. So like if you go traveling to Europe, sometimes you can't use your hair dryer or your appliances that were made for America with different voltage. Okay, so something to kind of keep in mind. But because the United States had that, they just had to keep that. Now, the good thing about 220 volts is that power can be transmitted more efficiently, and we'll talk about that a little bit later. But voltage, higher voltage, means lower current. It means safer current. I mean safer transmission, right? It can be sent at a lower current, higher voltage, and much safer. Okay, so sometimes in your house you will have 220 volt appliances. There is the power coming from the power company can be 220 volts, like your dryer, your stove, water heater sometimes might be on 220 volts. If you see the much bigger plug, that's a 220 volts. So obviously more dangerous, possibly because bigger potential difference, 220 volts there. Okay. So one other thing to add is if I want to convert from AC to DC, okay, this is actually something that has to happen. Sometimes, for example, if you're on a laptop right now, it has a battery, which means that your laptop really runs on DC. Right, so anything that runs on a battery is DC, but yet you have it plugged in to your AC house, right? But as you notice, there's a box, right? So you got your plug, right? And then you got a wire, and you got this box, and then it goes to the computer or whatever. This box is a transformer. Okay, transformers change voltage, right? So we don't want 110 volts going into our battery that might be 9 volts, right? So this transformer steps it down to 9 volts before it goes to the computer, right? But how are we changing this AC, which has a pattern like this, right, into a DC that has that? Well, what we use is what we call a diode. Okay, and all a diode is basically a valve that only lets electricity flow in one direction instead of back and forth like AC. Okay, and let's let me show you a picture of what that might look like. So let's go back here to this. I'll give you a couple little illustrations here. So AC, right, doing this. So if a diode is put in place and it limits the flow of electricity to one direction, it might look like this, right? It's only going to allow that part of the current to go through, right? And so what used to happen is if you went from AC to DC, you'd have this kind of choppy flow of power, and there would be these dead spots where no electricity was happening. Well, so there's two things they do. One is they would bring in a second diode and they would alternate them, and so it would fill in the gaps like this. But you still have these points here where there's like not very much electricity, right? And so what they do, as my last graph will show, if this was my original, actually I'll do a dotted line. Let me try that again. Let's say that we have, this was my normal flow. Sorry, I'm having problems here. Okay. That's still pretty choppy. And so what they did is they put a capacitor in there. And remember what a capacitor is it's basically a little tiny battery, right? It holds charge. And so with a capacitor, when the current got to this point right here, the capacitor could take a little energy from this point, store it in the capacitor, and then let it out at point 2. Right? So we're going to take a little electricity from point 1 and store it and let it out when it gets to point 2, and then same thing here at point 3 and point 4 and so on and so forth. And so what you actually get is a little, I'm not drawing this very well, but you kind of get the idea, right? It's a much more even flow of electricity with little ups and downs and not the big ups and big downs that normal DC is. So capacitors are put in there to hold on to some energy and let it out a little bit when it needs to, store it back in when it needs to. Okay, so that's how we convert AC power to DC power. Okay, all right. this last part we're going to talk about, I'm going to just kind of get it started. We're not going to finish it today because it's a little bit heavy and I want to make sure we understand it. All right. So when you complete a circuit, right, when you flip a switch to turn something on, you're completing a circuit. We call that circuit closed. Okay. And the light, I mean, I don't know if you've ever done this, but like try to race light. When I was little, I would stand at my door to switch off my light, and I would try to beat the darkness, right, to my bed. Well, obviously that doesn't happen because these things happen instantaneously. Same thing when you switch it on, right? The light bulb seems to come on instantaneously, right? That current is established almost at the speed of light. Now, why not at the speed of light? Well, there's some things in the way, right? There's particles, resistance. Okay. It is not the electrons moving at that speed. Okay. It is not the electrons moving at that speed. Now, electrons inside metal, they move very, very fast, right? But they don't make current. Like if I just have a wire and I'm just holding onto a wire, there's electrons in those wires are moving really fast, but there's no electricity, right? So it's not the electrons that are providing the electricity, right? Now, one reason is because those electrons are flowing within that wire, right? They're going in all kinds of crazy directions all at the same time, those free electrons. Okay. Now what happens is when you put a current through it, right? Now what happens is all those electrons, remember, they line up like in the electric field. Okay. And now that there's some organization to those electrons, now we get a flow of energy. Okay. So the establishment of that electric field inside that conductor is pretty important, right? And it definitely establishes a direction for those electrons, right? So they're not just randomly flowing in all kinds of different directions. They're working together, so to speak, in order to pass that energy through the wire. Okay. All right.